Hello, how are you doing? Thanks for watching. We're talking about spectrum of hydrogen. Spectrum of hydrogen. What is spectrum? Spectrum, a graph of light according to either frequency or wavelength. Spectrum shows a graph, is just a graph of light according to either frequency or wavelength. Now, dealing with the spectrum of hydrogen, I'll give you points that you got to know about the spectrum of hydrogen very sharply now. Let's go. Now, moderately low pressure is needed. Moderately low pressure is needed in dealing with the spectrum of hydrogen. An electric discharge tube placed through a gas. An electric discharge takes place through a gas. An electric discharge will take place through a gas. Then the third point I'd like you to get, the emission of gas. There must be emission of gas, and that emission of gas is depending on the characteristic of the gas you use. So if hydrogen you are using is on the characteristic of hydrogen. So in the emission of gas, you're talking about the characteristic of hydrogen if you are doing hydrogen or any other gas. Now another point you got to know that the spectrum of hydrogen is several distinct series of lines are found. Several distinct series of lines are found. The another point I want you to get here is the line spectrum of hydrogen atom is given by the equation. The line spectrum of hydrogen equation is given by the equation. I'll show you the equation now. It's given by this equation. Hope you can see this equation clearly. The line spectrum given by this equation, 1 over alpha equal to RB open brackets 1 over n you can see there n1 over 1 over n raised to power 2 then 2 down. So this equation is needed to determine the line spectrum of an atom. Very, very important. To determine the line spectrum of an atom, you need this equation. And I'll give you another format of this equation so that you see it clearly. Just be patient. This talks about the line spectrum. Talks about the line spectrum. To determine the line spectrum of hydrogen atom is given by this equation. You can see this equation clearly. This is a V, 1 over alpha equal to RB, then open bracket 1 over n raised to power 2 minus 1 over n 2 raised to power 2. The RB there represents the Rydberg's constant, which equal to 1.097 times 10 raised to power 6 meter per. Then the V power there means wave number, and it's measured in centimeter or meter. So here is centimeter or meter. Then the alpha, the Limber sign here is the sign of wavelength. Is that in centimeter or meter? Then your capital N here, it can be 1, it can be 2, it can be 3, it can be 4, just like that, depending on the level or the line of spectrum you are dealing with. Then the small n here represents any integer greater than capital N, which is the whole number. Any integer greater than the level you are dealing with, or level of orbiter you are dealing with, or line of spectrum. Okay, so that equation is used in determining the line spectrum of the hydrogen atom. Exactly. Now, in the hydrogen atom, in the hydrogen spectrum, the following series are observed. While dealing with hydrogen atoms, the following series are observed. You have the Lyman series, you have the Lyman series, you have the Barman series, you have the Paschen series, you have the bracket series, you have the P-form series. I'll come again. In dealing with hydrogen spectrum, the following series are observed. You have the Lyman series, you have the Barman series, you have the Paschen series, you have the bracket series, and you have the P-form series. Now, I'm giving you vital information on this series. I'd like you to get it clearly. In the Lyman series, this consists of all those wavelengths which are emitted when electron jumps from a different higher orbit to the final orbit with n, the small n, equal to 1. I'll come again. If dealing with the Lyman series, this consists of all those wavelengths which are emitted when electron jumps from a different higher orbit to the final orbit with the small n, equal to 1. The small n must be 1. Then if you have to look for other n's, the n1 must be 1 while doing Lyman series. Then the n2 can be 2. If you want to determine the n for the next line of series or line of spectrum of hydrogen, then n2, 3, 4, 5, and continues. So for the Lyman series, there's a question you are meant to use in determining the Lyman series to determine the wave number of the Lyman series. There's a question you are supposed to use. I will show you something now. In determining the Lyman series, you can see this Lyman series. Use this equation. the wave number equal to 1 over wavelength equal to ROB, open bracket, 1 over 1 raised to power 2 minus 1 over n2 raised to power 2, which equal to R, open bracket, 1 minus 1 over n2 over 2. I'll come again. This is the wave number of Lyman series. 1 over wavelength equal to ROB, the ROB constant. Then 1 over 2. This one is for the n equal to 1 for Lyman series. Then 1 over n2 raised to power 2 equal to R, open bracket, 1 over 1 over n2 raised to power 2. So with this equation for Lyman series, I use it to determine the wave number for Lyman series. Use it in determining the wave number for Lyman series. Okay. Now with this we go on. That's the Lyman series. Then the Lyman series, this series of wavelengths lies in the ultraviolet region of the spectrum. For the Lyman series, it lies in the ultraviolet region of the spectrum. Then the next series I would like us to look into while dealing with the hydrogen spectrum, the Barman series, the Barman series. The Barman series ends at the orbit or level with N2. It ends at the orbit or level with N2. Then another particular thing about the Barman series, all those electronic jumps that ends at the L orbital, all the electronic jumps ends at the L orbit or orbital, it ends at the L orbit or orbital, that's of level of the shell or orbit you are dealing with. Then there's a question you got to use in determining. But before I show you the equation you use, this region lies in the visible and near the violent region or solar spectrum. For the Barman series, it lies in the visible. For the Barman series, it lies in the visible and is near the violent region or solar spectrum. Now, this equation you use in determining the Barman series. Use this equation for Barman series. Use this equation, wave number equal to 1 over alpha equal to ROB, open bracket, 1 over the place of 1 for Lyman series. In Barman series, it will be 2. The n will be n1 will be 2 raised to power 2 minus 1 over n2 raised to power 2. Close it. Then open bracket, you have n1, which is 3. n1 which is 2, the n1 is 2. Then n2 can be 4 for getting the next level orbit, 5, 6 and so forth, but your n1 must be 2. So that this equation is used to determine the wave number of Barman series. Okay, now going on, the next series I'd like us to look into right now is the Paschen series. What's the Paschen series all about? This series in the infrared. This series is in the infrared region. So if you're talking about the Paschen series, it's mainly on the infrared region. The N1 will be 3. The N2 can be 4, 5, 6, 7, 8 to infinity. The N1 must be 3 because they're talking about the third level, N equal to 3. So the N1 must be 3. The N2 can be 4, 5, 6, 7, and 8, and so on and so forth. Then the equation you are meant to use for the Paschen series. I will show you the equation right now. This equation, you are meant to use it. You are meant to use this equation for the determination of the Paschen series. The wave number equal to 1 over wavelength ROB. Then the place of 2 for Barman series will be 3 for Paschen series. 1 over 3 raised to power 2 minus 1 over n2 raised to power 2. The n1 must be 3, n2 continuation of that 4, 5, 6, 7, 8. So that is the equation you can use to determine the Paschen series in the hydrogen spectrum. Now the next series we're going to look into now is the bracket series. This lies in the microwave region. The bracket series lies in the microwave region. It lies in the microwave region. That's bracket series, lies in the microwave region. Are you getting microwave region? Now the n1 must be 4. Then the n2 is 5, 6, 7, 8, 9, and so on and so forth. But the n1 must be 4, the level n equal to 4. So you're doing the fourth level of this line of spectrum, in the spectrum, the series. Now the equation you use is almost the same with other one, but the difference in the place of n1, your general equation for hydrogen. The place of this n, it will be 4. That's why if you look at this place, for the bracket series, the wave number equal to 1 over wavelength equal to ROB, open bracket, 1 over 4 raised to power 2 minus 1 over n2 raised to power 2, close it. Your n1 is 4, n2 5, 6, 7, 8, 9, and n. So this equation is what you use to determine the bracket series in hydrogen spectrum. Okay. Then the next The next series we'll be looking to in hydrogen spectrum is the p-fond. The p-fond series. The p-fond series. This lies in the radio wave region. The p-fond series lies in the radio wave region. The N1 must be 5. The N1 must be 5. The N2 is 6, 7, 8, 9, and so forth. So the N1 must be 5. So this p-fond series lies in the radio wave region. Then the formula we're going to use is this. For p-fond series, make use of this formula. The p-fond series, the wave number equal to 1 over wavelength equal to RB, then 1 over 5 raised by 2 minus 1 over N2 raised by 2. Close it. Your N1 must be 5, then N2 can be 6, N2 can be 7, you can push to 8, can push to 9, depending on the level you are dealing with. So these are equations you use to determine the series while dealing with the spectrum of hydrogen. I believe it's very clear to you. So I'm talking about the 5 series found in hydrogen spectrum. I'll list them for you again. You have the Lyman series, you have the Bowman series, you have the Armstrong series, you have the Brachy series, and you have the p-fond series. All of them with their equation determine when the region they are found. The region they are found, just like the Lyman series, is the series of wavelength lies in the ultraviolet region of the spectrum. Then for the Bowman series, it lies in the visible and is near the violet region or solar or the solar spectrum. Then for the Armstrong series, it lies in the infrared region of the hydrogen spectrum. Then for Brachy series, it lies in the microwave region of the hydrogen spectrum, while the last one, the p-fond series, lies in the radio wave region of the hydrogen spectrum. Thank you for watching. God bless.